Okay, welcome to this next video for Chem 161, elaborating further on some Chapter 3 content, where we'll touch on ideas behind the Pauli Exclusion principle, look at permutations, of the quantum numbers, and consider the implications for the electron and the orbitals for that electron. Okay, we saw in a previous video that we can assign the identity of an electron in an atom according to 4 principal quantum numbers, and the Pauli exclusion principle tells us that no 2 electrons can have the same 4 quantum numbers. So this is a way of us identifying, like we said a moment ago, the identity of an electron and associating analogously that electron an address, if you want. Every individual electron has its own unique address reflected through the options for the 4 quantum numbers. We saw that our principal quantum number, n, was what is used to determine the energy level of any subsequent orbitals. Okay, so the options now for n, like we have from Bohr's model from the atom, n can be any integer starting at 1, not including 0, and increasing. Okay, in principle, that can go to infinity. We see this principal quantum number and the n options reflected already here in our energy diagram for the orbitals that arise out of this concept. We see here that when we select the option for n equals 1, there is only one orbital called an s orbital. When n equals 2, we see 2 sets of orbitals, an s orbital and a new set of 3 p orbitals. And when we look at n equals 3, we'll see 3 sets of orbitals, a single s orbital, 3 p orbitals, and 5 d orbitals. So to help us distinguish s from p from d orbitals, we're going to need other quantum numbers. And to help us distinguish between one p option versus another, we'll use another quantum number to help us there. Okay. So with that, we can now see the value of the next quantum numbers. So the L angular momentum quantum number is going to help us describe the shape or the type of orbital. Okay, so based on the situation for n in question, we can determine what options L is allowed to be. Okay, so the rules for L are that it is, again, allowed to be an integer only, and those values for that integer can range from 0 through to n minus 1. So if we are talking about orbitals in, for example, the 3rd principal quantum number, the permutations allowed for L would be 0, 1, and 2, which is our upper limit because n was equal to 3. The parenthetical statement here becomes 2 in that case, so we can only be allowed 0, 1, and 2 for those L options. Okay. When we have examples like that, so for an L option that equals 0, we will assign this the letter that is S. So this will indicate an S orbital, which is spherical in shape. Okay, and we see one of those right above. When L is equal to 1, we will label this a P orbital. And these look like figure 8s, or sometimes I call them dumbbells. So that was for L equals 1. And when L equals 2, we will call those d orbitals. These mostly look like double dumbbells. Kind of like two of them crossed over together, as we see in our diagram here. 4 out of the 5 look like that double dumbbell structure. The middle one is very unique, and it has a donut shape and lobes above and below that plane of the donut. And lastly, when L is equal to 3, we will label those orbitals as F orbitals. And those are even more complex in shape. And we see those up here, some of which almost look like 3 sets of dumbbells overlapping. Okay, so already the L principal quantum number, the angular momentum quantum number, is specifying different shape options for the wave that is the electron in the quantum mechanical model for the atom. The last one that we want to use to help us understand which within an option, so which of the 3 p orbitals we are talking about, as you recall, is the magnetic quantum number, and this determines the direction of the orbital for an electron in question. So, for example, thinking about these 3 orbitals that arise out of the n equals 2 option, we know that the shape would be a figure 8 type orbital or a single dumbbell. And now we can specify between this one versus this one versus this one by specifying an m sub L value. Okay. And as we mentioned, there's going to be an m sub S quantum number, which is a spin quantum number. And there are only 2 allowable values here. So only one of 2 options. And that would be plus a half or minus a half. Okay, so with those ideas, we can take a look at a couple of examples now. And we could ask a question like, when n equals 2, what are the possible values of L. Okay, so perhaps we'd have an option like A, B, C, and D as a multiple choice question. We could have L as 0, 1, or 2 as a correct or incorrect answer to be decided by you. We could have another option that's 0 or 1, maybe another option that's 0, 1, 2, 3, or we could have L options that are only 1 and 2. So you should be able to use the rules on the previous slide about what we're allowed to do to determine possible L values based on an N value to help answer this question. So if you want, pause the video, see if you can work this one out, and then resume the video to check your answer, which we'll see in the next moments of this video. Okay, so, a way to approach this question might be to say, okay, well, I have an N of 2, so what are the allowable L values? So the L values that we know start at 0. They have to be only positive, and they walk up to a limit that is 1 less than the N value. So my two options there are 0 and 1. At this point, we've answered the question, and so we're done. We know that this is the correct answer, answer B. Let's just keep going a moment with the other rules to see if you can apply them. So M sub L values were allowed to be integers that are framed by the limits of the positive and negative of this upper value of L. Okay, so we can start at the low negative end. We are allowed -1. We have to go to an integer, so we are allowed to be 0. And we are allowed to be +1. Those are the allowable M sub L values. Okay, and then M sub S values, we said we can be either +0.5 or we can be -0.5. Okay, so just to give you an idea here, we knew from the Pauli exclusion principle that no two electrons can have the same 4 quantum numbers. So that is, we can say that one electron could have the following principal quantum numbers. We could have this as one electron. We could also have the next option for another electron. You can see that those two options have the same energy level. They have the same shape. They have the same direction or orientation of that orbital, but their spin number distinguishes them, as we see here in the bottom option. Okay. We could go further and do that again and say that another electron could have its identity described by, for example, 2, 1, 1.5, and a different electron has to have different quantum numbers. And so we might have something like 2, 1, 1 +0.5 instead of the -0.5. And that would be a unique electron as well. Again, those two orbitals and their energy level and their shape would be the same. They would be the two electrons are distinguished by their spin number. Good. Okay, so here's another question just to practice. So we could also say when L equals 4, what are the possible values of M sub L? That's another good question. And maybe some multiple choice options would be A, B, C, and D. And so we could have 0, 1, 2, 3 as an answer to consider, -1, 0, +1, 1 is 4, -3, -1, 0, 1, 2, and 3, and even 4 to finish off that option for answer C. And answer D, -3, -2, -1, 0, 1, 2, and 3. So again, this is a moment where you can pause the video, work through this answer, and answer this in your own notes, and then resume the video once you've had a chance to do that. Okay, so we know from our rules for what allowable options are for M sub L, that M sub L is framed by the positive and negative limits that are determined by L. So M sub L is allowed to start as low as the negative value of L and must walk up in integer values, including 1 and including 0. So we have lots of options there for the M sub L options. All right. So the answer here would be answer C, which would be the correct answer. Okay. So with those ideas, hopefully now you're seeing that we are able to associate the three-dimensional orbital that can be reserved for an electron, and the two electrons can be in the same sort of orbital energy level, the same orbital shape, and even the same orbital shape that's pointed the same way, and they can be distinguished by a spin value. We saw that in a few discussion points a moment ago. And hopefully now you're also appreciating how the complex set of orbitals that we have available for defining the electron, as we see in this diagram, may or may not be present according to these rules for permeating the quantum numbers, starting with n and looking at values for L, and then next looking at values for M sub L, and then thinking about finally spin options for the electron. So, for example, in the n equals 1 category, we are only going to see a spherical orbital present in that situation. When we have n equals 2, we know that we can have some options for shape now, as reflected through the options for L, being either 0 or 1. And now we can see that we're going to see those different shapes evolve. So now we can have either that spherical option, or we can have these figure 8 options. So those types of orbitals are available in the n equals 2 energy level category. Likewise, if we're allowed to go to the next energy level, reflected through an n equals 3, we now have 3 options for L, that is 0, 1, and 2, and this is going to give us options for a unique shape to now arise. That's here at the top value, and those double dumbbell type orbitals come out of that option, and they're reflected in the topmost value. Remember, we said when L was equal to 2 that we would call that a d orbital, so the d orbitals are the 5 options there that we see. And finally, to start seeing the most complex orbital shapes, the F orbitals, the 7 F orbitals that are available there, we have to have an n value of 4 to allow for 4 sets of orbitals as reflected through L values of 0, 1, 2, and 3. And so these orbital options come out of that, and that's where we get all possible shapes that can come out. Okay? This ends up being like a little bit of a framework for us. So we now know that all these little lines in this energy level diagram, with higher energy values being higher on the chart, we see those arising for things like the n equals 4, and the more complex shapes there are highest in energy. And when we are allowed to put 2 electrons into each of these energy spots, so we are allowed to put 2 electrons here, and we can distinguish between those 2 electrons going there because we are allowed 2 different M sub S options. And that's how we build up the atom using quantum mechanics and respecting the laws that electrons can behave as waves and can also behave as particles when they are considered as material ejected from metals, as we see in some classic experiments reflected in your textbook. Okay, please email me if any of this is not sitting right. And